Hello class, and thank you for watching the last part of lesson 5.3, polynomial functions in the graphs. In this last section, we're going to go over the effects of the multiplicity of the zeros, which is talked about in the previous example, and also the end behaviors of graph. So we're going to talk about the behaviors of the polynomials, specifically the polynomial functions, how the end behaviors of these polynomial functions look like, and how the multiplicity is going to affect the x-intercept in terms of what that looks like on a graph. So we're going to start with multiplicity and their x-intercept. Now recall that if a polynomial function contains a factor in the form of x minus c and is raised to a power, we're going to call it p this time, the behavior near this x-intercept, this value of x equaling to the opposite of this number, is going to be determined by, again, its multiplicity, by this power of p. The graph of a polynomial function is going to be tangent to the x-axis, which means it's going to touch the x-axis and bounce off at this zero, at this x equals c, when that p number, when that power of p is an even number. And the graph of the polynomial function will cross the x-axis, intersect the x-axis at that zero when p is an odd number. So the behavior of the function, again, depends on whether that number is going to be an even or odd number. So let's try to analyze again what I'm trying to say here. So here I have the graph of x minus 2. So you see I'm crossing the x-axis at 2, at positive 2. Again, the opposite of that number, minus 2. So that means that x equals to positive 2. And notice that the power of p right now is the value of 1. So as you can see, again, the graph is crossing the x-axis at this location. We see that the graph is below. So on the left of this point 2, 0, the graph is below the x-axis. But then to the right of this point, the graph is above the x-axis. Now, check out what happens to this number if I keep it as an odd number. If I change that power to 3, notice that obviously the graph changed because it's a different type of polynomial function and it curves, but it still intersects the x-axis at 2, but on the left side of that point, notice that the graph is below the x-axis. We get to the x-intercept and move beyond it and move above it to the right. So it's again crossing the x-axis at that value. And as long as I keep that exponent an odd number, like 5 and 7, it's going to behave the exact same way. Now the graph does change a little bit. Obviously, it's going to have to change because the power is different. But in terms of the behavior of the graph, it behaves the same way. It crosses through. You will notice that the larger the exponent, let me zoom in, the flatter the graph is as it approaches this point of intersection. Okay, you can see again that it's a little bit flatter. Compare that to 3. Notice it's not as flat. 9 a little bit more flatter. 5 less flatter than 9, and 7 is a little bit flatter than 5 but less than 9. And if I do 21, let's say 21, again, notice that it's still going to cross. It looks more like upwards letter Z or S, okay, like it's been rotated, but it still crosses. That's the key thing. I want you to see that it crosses. Now compare that to being an even number. Let's say that the power is an even number. This is referred to as tangency. The graph is going to touch the x-axis, but instead of crossing through and moving to the opposite side of the x-axis, which right here would be, notice that we're above, we're moving downwards, and instead of continue moving downwards, it touches and bounces off. This has to do with this exponent up there being an even number this time. So let me change it to another even number, like 4. Notice that it behaves the same way. Of course, it's going to have the similar effect in terms around here. It's going to be more horizontal, becomes flatter. But 6, still tangent. 8, still tangent. And 10, still tangent. So as long as that exponent is an even number, this is what I'm referring to when I say that the graph is going to be tangent. It's going to touch the x-axis and turn back around, which means that it's going to, the y values in this situation are going to stay positive. Notice that every single point on this graph right here, see if I can find points. Notice that all these y values are all positive. These are positive still. They get very, very close to 0. And then again, when they move away, they become more positive. So let me change this to a 2 so it's not so flat. See, positive y values, I get to 2, the y value becomes 0, but then when I move away to the right, the y values are still positive. So having tangency means that the y values are going to stay the same sign both on the left and on the right side of this x-intercept. Now, because I want to focus on this idea, this concept, we're not going to practice any factorization skills. All of our polynomials are going to be in the factored form. So we have to identify what the respective zeros are and what effect the multiplicity is going to have on the graph at that said 0. So let's review how to find the 0. So here we want to figure out what's going to make this equal to 0. So that would mean that 1/2, that factor doesn't equal to 0, so we don't have to worry about that. X plus 1 needs to equal to 0, and 2x minus 3 needs to equal to 0. The multiplicity of this one is going to be 1 because it's raised to the first factor, and the multiplicity of this one because it's raised to the second power is 2. So here, odd number, and the multiplicity here is an even number. So let's figure out what the zeros are. Well, the 0 for the first one, this one doesn't have one, so we don't have to worry about that. But this one has a 0 of -1. Now, what's going to be the effect of the graph without having to graph this? What's going to happen at x equals -1? Well, since the multiplicity is 1, an odd number, that means that the graph of f of x will cross the x-axis at this 0. So that is the effect of it. And that again has to do with that number being an odd number. Now, what's the other 0 here? Well, to find the 0 of this one is going to be a 2-step. We're going to move the 3 to the other side, making it +3, and then divide it by 2. So that would mean that the x-intercept for this will be +3 divided by 2. Now, since the multiplicity is 2, an even number, again, we don't care about the value of the 0. We care about the multiplicity in order to determine the effect or the behavior of the graph as it approaches or as it reaches again this x-intercept. So since this number is an even number, now like I said with this one, the multiplicity is even, then that means that the graph of f of x is tangent to the x-axis at x equals to 3/2. And that's it. So if we were to graph this, we would see exactly that. So here we have the graph again like of f of x. Again, notice that the 1/2 doesn't affect where it crosses the x-axis because that term, or that factor, does not have an x on it. So the x plus 1 crosses the x-axis right here at -1. And because, again, the multiplicity is 1, like I mentioned, this is what I mean that it's crossing. Notice that on the left of that point, it is below the x-axis, but then to the right of this point, that point is above the x-axis. And if we look at the y values, notice that right now the y values are negative. When I get to 0, the 0, -1, the y value is 0, as you see right there. But as soon as it moves to the right and get a value, an x value that's bigger than -1 to the right of that, notice that all my y values are now positive. So they're all going to stay positive. And then when I approach this x-intercept right here, okay, all my y values are positive, then they become 0 at 1.5, which is again the number 3 divided by 2, but they stay positive when I move to the right. So you see, the y values don't change signs. So if something is going to cross the x-axis, the y values are going to change from positive to negative or from negative to positive. But when it's tangent, the y values stay the same sign. So if it's positive on the left of the x-intercept, it's going to stay positive on the right of the x-intercept if that x-intercept, again, has a multiplicity of an even value of 2, 4, 6, 8, etc., etc., etc. So how cool is that? So let's look at the next example. So right here we have -4. We want to figure out what's going to make this equal to 0 first of all. So -4, since this doesn't have an x value, obviously that can equal to 0. But our x plus 2, that factor can be made equal to 0. And x minus 5, that can also be made equal to 0. And the respective multiplicities for each one is x. I'm sorry, let's talk about the multiplicity. The multiplicity of this factor, since it's to the second power, our multiplicity is 2. And since this one's 3, our multiplicity is 3. So what are the zeros? So the zeros first is that x equals to -2, which means that because we have an even multiplicity, the graph is going to be tangent at that location, at x equals -2, not +2. And the other zero is +5, and because +5, or the factor of x minus 5 is raised to the third power multiplicity to an odd number, that means that at x equals 5, the graph crosses the x-axis at x equals +5. Let's look at two more examples. So right here, let's find the zeros. So 2x equals 0, x minus 2 is equal to 0, and x plus 5 equals 0. The respective multiplicities, I'll write those on top. The multiplicity of this factor is 1. The multiplicity of this factor is 2. And the multiplicity of this last factor is 3. Or power. The power of each of those factors are 1, 2, and 3 respectively. To make this equal to 0, I just have to divide by 2. So x is equal to 0. Which means that the graph is going to cross the x-axis at the location because the multiplicity is an odd number. Since at x minus 2 we have the power of 2, the multiplicity is going to be an even number. X equals to +2 means that the graph is going to be tangent at that location. And the last one has a 0 at -5, and since the multiplicity is an odd number, the graph is going to cross the x-axis at that location. And for the final example, we have -6x to the third power. We're going to see what makes that equal to 0. X plus 4 equal that to 0. Oh, I don't need the 3 right there. I don't know why I wrote 3. And x minus 1, set that equal to 0. So the multiplicity when we solve this will be 3. When I solve this equation, the multiplicity is 5. And the 0 for this one is going to have a multiplicity of 4. So x is equal to 0, and with an odd multiplicity means that the graph is going to cross the x-axis at that location. For x plus 4, the opposite of that is -4, and it's going to do the exact same thing since the multiplicity, again, is an odd number. Pay very close attention. Again, I don't care about this number being even or odd, because that's a lot of things people mess up on. They confuse what we're looking for in order to determine if the graph is going to cross or be tangent at these locations. We're looking at the multiplicity, the power to the respective factor. So don't get caught up on determining if this is even or odd. We don't care about that. We care about the exponent being even or odd, okay? And on the last one, x equals -1 means that x equals +1. And since that multiplicity, that power is an even number 4, that means that the graph is going to be tangent at that x-intercept. So it's going to touch 1 and then bounce off. And whether it's the y values are, or whether the graph is below or above, your y values are positive or negative, that's going to be irrelevant right now. We just want to focus on, okay, what's happening at that location, okay? All right, let's go a different approach now. Let's talk about how to identify the zeros and determine whether that zero is going to have an even or odd multiplicity. So the zeros, recall, are going to be anything that intersect the x-axis right here which is at the point of -3, of -1, and at +4. Now, of those three, which one is going to have an even multiplicity, and which of those is going to have a multiplicity that's going to be an odd number? So we know that the factors are going to be x minus a -3, so x plus 3, x minus a -1, so x plus 1, and x minus 4. Now, what are the respective powers for each one of these factors, aka their multiplicities? Are they going to be an even or odd number? This all depends again on the behavior of the graph. Since this graph right here is tangent at this location, notice how it touches the x-axis and bounces off, then I know the multiplicity at this location, which is at x plus 3, or I'm sorry, x equals -3, that has to be an even number. So I know x equals -3 has to have an even multiplicity. Now the other two locations are not tangent. Notice how the graph crosses the x-axis. Notice that here the y value of this point right here has some positive x value and a positive y value. But then as soon as you move across this point of intersection, the x-intercept, this point there has the x value is negative, a negative x value, and the y value is negative. You see that change in the y values? We don't know exactly what that number is, but we know it's positive because it's above the x-axis. But then over here, as soon as we move to the right of this x-intercept, the y value is negative. So that means that it has to have an odd multiplicity. So x equals -1 has an odd multiplicity. It means that the factor of x plus 1 is raised to the power of 1, or maybe 3, or maybe even 5. I don't think it will be that high because, again, the curvature doesn't look to be relatively fat. It looks like it's just going through. So that looks like a multiplicity of 1, an odd number. And the same thing is happening here at this location right there. Let me zoom in. So notice that at this location, let's look at what's happening to the left and to the right of this x-intercept, like in this point right there. At this point, we have a positive x value, and the y value is some negative number. Again, so this is at 3. Let me pick that point right there, exactly at 3 instead. This point right there, we know for sure that the x value is going to be +3, and we know that the y value has to be some negative number. So we have a negative y value. But then when we look to the right of 4, let's say at this point right there, where the x value is +5, we can clearly see that the y value, according to this, looks like it's going to be exactly 80, +80. So you see it changes from a negative number to a positive number there. So that means that this is crossing, okay? So if you're not sure what it means when I'm crossing and still can't see that, look at the y value. See if to the left of the y value, the sign changes when you move across the x-intercept, and the y value changes from a negative to a positive, or from a positive to a negative. That means we're crossing the x-axis. So because of that, this x equals 4 needs to have an odd multiplicity. So x equals -4 is also going to have an odd multiplicity. So let's look at this example now. Let's first identify our x-intercept. So we have here, I'm going to do all in blue. We have one right there, x equals -5. Our x-intercept right there at -1, and then another one right there at +3. So which one has even multiplicities, has an even multiplicity, and which one is going to have an odd multiplicity? Well, let's look at the behavior. Well, since we're crossing the x-axis there, that means that the multiplicity at x equals -5 is going to be an odd number. This right here is tangent. Our y values stay positive in that section right there. So x equals -1 is going to have an even multiplicity, and the same thing right here. This is tangent. It touches and then bounces off. So x equals +3, that's a +3, is also going to have an even multiplicity. And for the last example, our zeros are -6, 0, and +6. X equals -6, 0, and +6, like I said. And the only one that has an even multiplicity is the center one, because this one is going to touch and then turn around. So x equals 0 is going to be raised, or the factor of x is going to be raised to an even power. So x equals 0 is going to x is going to equal to 0 an even number of times. And x equals -6 and x equals +6 have odd multiplicity, since the graph, again, is intersecting and crossing through the x-axis. So it moves from below to above, and on this side it moves from above to below the x-axis. So that means that they have to have an odd multiplicity. And we're going to finish off these notes talking about the end behavior of polynomial functions, which is, like the statement says, is the way the graph behaves towards the very far left and the very far right at the ends of the graph. So the behavior of the graph of the function to the very far left and to the very far right are called end behaviors, or in this case, end behavior, singular. Although the graph of a polynomial function may have intervals where it's going up or down, increasing or decreasing, the graph is eventually going to rise or fall without bound as it moves to the far left or to the far right. Now, the way we determine the behaviors, again, the end behaviors of the graph without relying on the graph, is by using the leading coefficient test. So like I mentioned again, your polynomial, so here's an example, I'll go through this right now, but your polynomial is going to end up doing one of these four things, okay? Yes, it's going to curve up and down and have intervals where it's going up and then down, crossing, again, the x-axis, being tangent to the x-axis, but eventually every single polynomial is going to do one of these four things here. The ends are going to be either pointing in the same direction or opposite direction. Now, the way we do this and figure this out is by using the leading coefficient, the term at the very front, and by looking at what this exponent is there. I normally start with what's happening on the right side, and I'll go through the steps on how to determine. But if this number appears an odd number, then that means that the two ends are going to be pointing in opposite directions. One is going to be pointing to the right, and the other one is going to be one of them is going to be pointing upwards, rising, and the other one's going to be pointing downwards, falling. And it all depends again on that leading coefficient as well. If that leading coefficient is a positive number, that means that the right side is going to be pointing up and the left side is going to be pointing in the opposite direction. So think about it like y equals mx plus b. If your m again is a positive number, the line goes upwards. You see right there how this end is upwards and this end is downwards. It's exactly like that. So we're just focusing on that number there. If that number happens to be a negative number, and I think about this as a line, then the right side is going to be going down, and the left side, because it needs to go in the opposite direction because this is odd, will be moving upwards. Now, if that polynomial has a degree that is an even number, so that largest exponent is an even number, then the two sides are going to be pointing in the same direction. And if that number is positive, then the right end points up and the left end points up. But if that leading term is a negative number, then the right end points down and the left end also points down. And that's the way, again, I try to memorize this and do this, and finding the end behavior using, again, this leading coefficient. First determine what the right end is doing and then the left. So for example, for a polynomial function, is the easiest way to find the end behavior, like I said, is for the right side first. The right side is going to go upwards, again, rise, if the leading coefficient a sum n is a positive number. But it's going to go downwards, fall, if that leading coefficient is a negative number. And then after determining whether the right side goes up and down, I can figure out what the left side is doing because of that exponent on that degree, the degree of the polynomial. If the degree is an even number, then it's going to do the exact same thing as the right side. But if that degree is an odd number, then it's going to go in the opposite direction of whatever the right side is doing. And that's an easy one to memorize because using mnemonic devices, O, opposite, O for odd. So let's look at these 4 examples right here, okay? So like I said, the first thing we're going to do is determine what's happening on the right side, and then we can figure out what's happening on the left side. So to determine what's happening on the right side, we're going to look at the leading coefficient. We're only going to focus on this term right here. So f of x is equal to 1 x to the 4th power, and we don't care about anything else. Since this number is a positive number, then I know the right side is going to go upwards. And since this number is an even number, then that means that the left side is going to go in the same direction and also rise as well. So which means as x is approaching positive infinity, your y values are going upwards, and as x approaches negative infinity on the left, your y values are also going upwards. So for this example, the next example, example B, again, just focus on the first term. So negative 6x to the 3rd power. All this other stuff is just going to make the graph, again, in the middle, on the in between negative infinity, as x approaches negative infinity and positive infinity, it's just going to simply make it go up and down. We care about what's happening on the very far right and on the very far left as this polynomial moves up and down. What ultimately is going to occur at the end. So because this number is a negative number, so first again with the right side. Since that number right here, the leading term, has a negative coefficient, that means that the right side is going to go downwards. And since this number is odd, that means that the left side is going to go in the opposite direction. Odd for opposite. So using arrow notation, that means that as x approaches positive infinity, the y value is moving downwards to negative infinity. That's the right. And on the left, maybe I should do this from left to right. On the left side, so as x approaches negative infinity, your y values are going upwards. And on your right, using arrow notations, as x approaches positive infinity, your y value is moving downwards towards negative infinity. Moving on to example C. So for example C, similar situation, we just care about that first term. Since this is positive, that means that the right side is moving up. And since this number is odd, that means that the left side is moving in the opposite direction, so down. So using arrow notations, the left side, which is when x is approaching negative infinity, your y values are moving downwards, so towards negative infinity. And on the right, that's when x approaches positive infinity, where your y values are moving upwards, so positive infinity. And then finally the last one, so set negative 7x to the 6th power. So since this number is negative, that means that the right side is moving downwards. And since the degree of this thing is an even number, the same. It's going to move the same direction as the right, so also downwards. So in arrow notation, the left side as x approaches negative infinity, the right side is when x approaches positive infinity. We can now determine what's happening to the y values. The y values are both decreasing, so they're both going towards negative infinity. So again, they're both pointing downwards. And we can use this information also, given a graph, to determine again at least what the leading term is going to be. We can also then use the x-intercepts, things like that, and determine again the actual polynomial from that situation, which we'll do later. Right now we're just going to be focusing on that leading term. Well, since the two ends are pointing in opposite directions, as you see right here, we have this end and this end pointing in opposite direction. I know that the degree has to be an odd number. And because of the number of turns, 1, 2, I recall from the first lesson 5.1, that means that the degree has to be specifically at least 3. 2 plus 1 is equal to 3. So you see an odd number. Now, what about the leading coefficient? Well, since the right end is pointing downwards, that means that the leading coefficient has to be a negative number, has to be a number less than 0. We're going to assume that that negative number is going to be simply between -1 or +1. So when it's negative, we'll say it's -1, and if it's positive, we'll say +1. So this polynomial function, f of x is equal to a n times x to the power of n plus all the other terms until we get to the constant, a sub 0. We'll know that this term has to be a negative number, so we'll say -1. And the degree here would have to be at least 3. So we'll say 3 as the least possible one. So this is what the first term to this polynomial will look like. Then we can also use the zeros and all the other stuff again to figure out what the rest of the polynomial looks like. But right now we're just going to simply focus on that. So for the other example, same scenario. Since this end again is pointing, the two ends are pointing in the same direction, I know that the degree has to equal to some even number. And to figure out exactly what the minimum value would have to be, what minimum even number has to be, I'm going to look at the number of turns, 1, 2, 3, add 1 to that, so I know that that degree would have to be at least 4. Okay, it can be 2, even though 2 is an even number. It cannot be 2. It would have to be bigger than 2 because of the number of turns. And now, since the right end is pointing upwards, I know now that the leading term has to be a positive number. So for this polynomial function, which in standard form is written like this, I know that this number would have to be a positive number. We'll assume it's +1 and not some other number. And the degree would have to be at least the even value of 4. It could possibly be 6, okay? But we'll assume that it's going to be the lowest possible degree. So the lowest even possible degree would have to be 4 here because of the number of turns. So there you have it. So this finally concludes again this section on polynomial functions and their graphs. The zeros of the polynomial functions, 5.3. If you have any questions, please again reach out. Any problems on the homework, again, check out the videos associated with that homework, or you can simply click on message your instructor there through My Open Math. Like always, I appreciate you watching, and I hope you have a great day. Goodbye.